We're now going to look at B7. In B7, we have computing the limit as x approaches 0 of x sine x. And the challenge we have is sine of 1 over x. And if x approaches 0, that's kind of like x approaching infinity and x approaching minus infinity. Because if we approach infinity, as x approaches 0 from the positive, this number gets really big. And as x approaches 0 from the negative, this number gets really big in the negative direction. It's kind of approaching both at the same time. And if we look at the sine function, it's a sine curve, and it never converges. So it is what we call a divergent limit, but it's an oscillatory limit. So because it's oscillatory, that sine of 1 over x will never go to a number. So the challenge is, how do we deal with this? Well, what we need to do is we need to create some sort of bound. So that idea of bounding it should bring into mind squeeze theorem. So squeeze theorem should be like popping in your brain. Okay, I need to squeeze it somehow. Now with squeeze theorem, what we need to do is we need to bound the function and then take the limits of the bound. To bound the function, first thing I'm going to do is x sine of 1 over x is less than or equal to the absolute value of x sine 1 over x, which is equal to the absolute value of x times the absolute value of sine x, which is less than or equal to the absolute value of x times 1 as the absolute value of sine of x is less than or equal to 1. Now this equals absolute value of x. Also, absolute value of, or sine x, or x sine 1 over x is greater than or equal to minus absolute value of x. Absolute value of x sine 1 over x, which equals minus absolute value of x, absolute value of sine over x, which is greater than or equal to minus absolute value of x times 1 as sine of 1 over x is less than or equal to 1, which equals minus absolute x. Thus, minus absolute x is less than or equal to x sine 1 over x, which is less than or equal to absolute value of x. So we've bounded the function. Now we also need to take the limit of the bounds. The limit as x approaches 0 of minus absolute x equals minus 0 absolute of 0, which equals 0. The limit as x approaches 0 of absolute x equals the absolute of 0, which equals 0. Okay? Now we've got the limit of the two bounds. How do we combine these two ideas? Well, we need to reference squeeze theorem. And in squeeze theorem, it says, let f of x be less than g of x be less than h of x for all x. And the limit as x approaches a of f of x equals the limit as x approaches a h of x. Then the limit as x approaches a of, this equals L. Then the limit as x approaches a of g of x also equals L. So in order to use squeeze theorem, we need to show the first condition and the second condition are met. So as minus x is less than or equal to sine 1 over x, which is less than or equal to the absolute value of x. And the limit as x approaches 0 of minus absolute x equals the limit as x approaches 0, absolute x equals 0. Then, so the first two conditions are met. So we say then, by squeeze theorem, the limit as x approaches 0 of our middle function, x sine 1 over x, must also equal the limit L, which is 0. And we have our solution. In B8, we show that the derivative with respect to x of cos of x equals minus sine of x, using the definition, the limit definition of the derivative. So the derivative is going to be the limit as h approaches 0, d by dx cos of x equals the limit as h approaches 0 of cos x plus h minus cos x all over h. I now need to use double angle formula here. Well, this equals the limit as h approaches 0 of cos x cos h minus sine x sine h minus cos of x all over h. And this here is my double angle formula for the addition. Well, this equals the limit as h approaches 0. I'm going to collect like terms on the top. So cos x cos h minus cos x all over h plus or minus the limit as h approaches 0 of sine x sine h over h. Well, this equals cos of x times the limit as h approaches 0 of cos h minus 1 over h minus sine of x times the limit as h approaches 0 of sine h over h, which equals cos of x times 0, as we showed, minus sine of x times 1. And these are fundamental trig limits. Cos of h minus 1 over h and sine of h over h. So this equals minus sine of x. We have our solution.